Hi, my name is Emily Thomas. Today is May 24th, 2022, and today I'll be presenting my Case Connections Unit 4 assignment. In this video, I'll be presenting cases 1 and cases 2. In this scenario for case 1, we have a newborn girl who, within 24 hours of birth, developed lethargy, hypothermia, and apnea. Labs ordered revealed that her initial blood ammonia level was significantly elevated at 314 and rapidly rising. The attending physician suspects a metabolic disorder, and in order to come to a proper conclusion of what disorder she's presenting with, we must first understand the normal mechanisms that should be occurring in the body with relation to ammonia. In a healthy person, the body works to metabolize nitrogen to avoid accumulation of ammonia in the body, as ammonia is highly toxic. The nitrogen, through a series of reactions, is converted to urea via the urea cycle and is eventually excreted through urine. First, nitrogen is transferred from an amino acid to an alternative keto acid through the use of transaminases. For example, we have the reaction alanine plus alpha glutarate through the use of a transaminase yields pyruvate plus glutamate. This initial reaction is what connects nitrogen transport to gluconeogenesis. As glutamate continues on through a series of reactions to result in free ammonia for the urea cycle, the pyruvate is sent to undergo gluconeogenesis, a fasted state process. And through a series of redox reactions and interactions with pyruvate kinase, phosphofructokinase 1, and glucokinase or hexokinase, we produce glucose. Next, in this nitrogen metabolism process, glutamate dehydrogenase works to convert the glutamate into alpha-ketoglutarate and ammonia, while also reducing NADP to NADPH or NAD to NADH. This enzyme works reversibly too. This alpha-ketoglutarate produced will then be metabolized by the TCA cycle, forming ATP. The next step involves glutamine synthetase, which primarily functions in peripheral tissue to pick up the ammonia produced in the previous step, combine it with glutamate, and convert the glutamate to glutamine. Glutaminase in the liver will then convert the glutamine back to glutamate, freeing the ammonia. This ammonia will then enter the urea cycle. In this patient, the elevated ammonia levels indicate that there is a deficiency in the excretion of this free ammonia produced through this nitrogen metabolism process. Now, upon further testing done, the patient was also noted to have elevated urine orotic acid levels, but low normal citrulline levels. In order to understand these findings, we must delve into the normal process of urea biosynthesis. In a healthy person, the newly freed ammonia combines with CO2 using the regulatory enzyme carbamyl phosphate synthetase 1 to form carbamyl phosphate. This enzyme, carbamyl phosphate synthetase 1, is allosterically activated by N-acetylglutamate, and N-acetylglutamate is activated by arginine. The significance of this will come up later. The carbamyl phosphate will then combine with ornithine using the enzyme ornithine transcarbamylase to form citrulline. Citrulline then adds on an amino group from aspartate using the enzyme arginosuccinate synthase to form arginosuccinate. Arginosuccinate will then be cleaved using arginosuccinate lyase to form fumarate and arginine. Finally, the arginine will be cleaved using the enzyme arginase into urea and ornithine, which will be recycled back into the mitochondria for this same process again. The urea will be sent to the kidney to be incorporated into urine. Now back to the further testing results we obtained, the patient was noted to have elevated urine orotic acid levels and low normal citrulline levels. The significance of this is that urine orotate comes from an alternative pathway involving carbamyl phosphate, and the enzyme carbamyl phosphate synthetase 2. Carbamyl phosphate can thus be used for the process of pyrimidine synthesis and present as elevated urine orotate or orotic acid levels. So to reiterate, there is no deficiency in ammonia synthesis proven by the high levels of ammonia in circulation, and there is no deficiency in carbamyl phosphate synthetase 1 as there is enough and more carbamyl phosphate. The issue is that the carbamyl phosphate isn't being converted to citrulline, which demonstrates a most likely deficiency in ornithine transcarbamylase, the enzyme. The least likely enzyme to be impaired in this situation is carbamyl phosphate synthetase 1, as again, there is an abundant amount of carbamyl phosphate. As a result, arginine becomes an essential amino acid as it can provide a separate pathway to form citrulline to keep the urea acid cycle going. Now on to case 2. Case 2 provides us with 3 different scenarios, and we have to determine the most likely enzyme deficiency. So for scenario 1, the finding of branched chain amino acids in a screening test helps us to focus on this specific form of metabolism. Our branched chain amino acids are leucine, isoleucine, and valine. These amino acids serve as the primary energy source for skeletal muscle. The metabolism of these amino acids begins with a transamination to a keto acid, which allows for the removal of the nitrogen group. The keto acid then undergoes an oxidative decarboxylation reaction through the branched chain alpha keto acid dehydrogenase complex. This reaction converts the branched chain amino acids into succinyl-CoA, acetyl-CoA, and acetoacetate, depending on which amino acid is involved, as well as produces NADH and FADH2 for energy. The elevated level of branched chain amino acids demonstrates that there is a deficiency in the enzyme involved in the oxidative decarboxylation reaction, which is the branched chain alpha keto acid dehydrogenase, which results in the branched chains not being metabolized. This deficiency is consistent with the diagnosis of maple syrup urine disease. Since there are no other amino acids involved in the above stated reactions, no other amino acids become essential as a result of this deficiency. Treatment options for this condition would include management of diet, meaning protein restriction, and avoiding conditions that exacerbate protein catabolism, such as fevers and dehydration. Thiamine supplementation may also be useful in this condition as it is a necessary cofactor for this oxidative decarboxylation reaction. In scenario 2, the clinical presentation of this patient is consistent with signs of alkaptonuria. In this condition, there is a deficiency in the enzyme homogentisate oxidase. This enzyme is related to the metabolism of the amino acid tyrosine. The deficiency leads to decreased metabolism of tyrosine, resulting in elevated levels of homogentisate, which is spontaneously converted to high levels of alkapton and results in alkaptonuria. Like in scenario 1, there are no other amino acids involved in this reaction, as this enzyme deficiency only becomes an issue after phenylalanine is already converted to tyrosine, and therefore no other amino acids become essential as a result of this deficiency. There are early reports of the use of nitisinone to be a therapeutic agent for this deficiency, but research is limited at this time. Finally, for scenario 3, based on the finding of elevated phenylalanine level, we can infer that there is a deficiency in the enzyme involved in the metabolism of phenylalanine to tyrosine, which is the enzyme phenylalanine hydroxylase. This enzyme also requires the cofactor BH4. The ultimate goal, starting with the metabolism of phenylalanine, is to form tyrosine, which can then further be broken down into fumarate and acetoacetate, which are important substrates for other metabolic processes. Because of this connection, tyrosine would become an essential acid in the case of this deficiency, so as to continue the metabolic process to form fumarate and acetoacetate. Supplementation of tyrosine would be useful for this condition if the enzyme was the deficiency in this case. In addition, the supplementation of the cofactor BH4 would also be important, as it is required for adequate enzyme activity. Thank you.